An open tube is a tube that is open at both ends, which are most wind instruments like clarinets, saxophones. They have pressure nodes and therefore displacement antinodes at the ends. So here's the ends. And what are we showing here? We're showing antinodes at the ends, so that's the displacement of the air. The air displacement behavior within the tube for the first three resonating frequencies is shown below. And let's just erase this here. Here we fit half a displacement wave inside the tube. So the wavelength is twice the length of the tube. That's what L stands for. That's the length of the tube. So therefore the frequency is velocity over lambda, so it's velocity over 2L, and that's our fundamental frequency. Now we go to the next one where we fit an entire wave, again with the displacement antinode at each end. In this case the wavelength is equal to L. So the frequency will be V over lambda, V over L, and it's twice this frequency here, the fundamental frequency. And then we go to the next step where N is equal to 3, and we have the third frequency. These are the resonant wavelengths and frequencies for an open tube. We showed these three on a previous slide, and we have lambda n, where n is the number of the resonant frequency, equals 2L, the length of the open tube, divided by n. Our first frequency, the fundamental frequency, is V over 2L. Then the second resonant frequency will be twice that. The third resonant frequency 3 times this one here, the fundamental frequency. So we can generalize that F sub n is equal to n times the fundamental frequency F sub 1, and n is the number of displacement nodes. If instead of air displacement, which is what we've looked at so far, and that's this column over here, you look at air pressure variation, the nodes and the antinodes are switched, and n equals the number of pressure antinodes. So let's go through this. Our first harmonic, or the fundamental frequency, in this case this is what we did before, n is the number of nodes. So what do we have here? We have one node, and you see here F1, F sub n is equal to F sub 1. So that is our first harmonic. Now if you go over to the air pressure variation, you can see that we have one antinode. Let's go to the next one. Lambda, where this case, lambda 2 equals L. You have one full wavelength fitting inside this tube. So in this case, let's look over here at the air displacement. How many nodes do we have? 2. So we use n equal 2. Go over to the air pressure. How many pressure antinodes do we have? Well, 1, 2. So can you see how it corresponds there? We've got 1 equals 1, and we have 2 equals 2, and this would be our second harmonic, and this is way too busy, so let's get rid of some of this stuff here. Second harmonic, which is where n is equal to 2. Another name for that is the first overtone. Right? Another name for the first harmonic is fundamental, then first overtone, second overtone, etc. Or you can call it first harmonic, second harmonic, third harmonic. An open tube has the same harmonic structure as a string. Here's our string being plucked over here. And this is why we switched to an air pressure plot on the previous slide. Here's the air pressure picture. And hopefully you can see how that exactly matches what's going on with the string for n equals 1. Then you go to n equals 2, where you fit a whole wavelength into the length of the pipe, and that works just the same for the string.